Yes, we can.
Okay. All right, guys. So last week we completed the chapter 4, which was network layer. Now we move on to the fourth layer, which is the data link layer. So today we're gonna cover some part of this layer, which is data link layer. Okay, as usual, first we start with the main objective of this link layer. What are the main jobs that we do in this layer? First of all, we're gonna understand the main principles of these link layer services. What are these services? So we start with the error detection and correction. As you know, when we transmit the information in terms of binary bits, right? During the transmission, these bits can be flipped or disrupted. So bit 1 can be bit 0 and bit 0 can be bit 1. And we experiences error at the receiver side. So we need to detect these errors, bit errors, and try to correct these errors in order to reconstruct the information, which can be in the form of video, voice, and text and data. So we perform some part of the error detection and correction at this link layer. That's the first, one of the main job of this layer. The second and very important part of this layer is the multiple access, because in the wireless, in mobile networks or in regular networks, we have a multiple user and we have a limited number of resources. So these multiple users they try to connect simultaneously to these resources, right? In other words, the multiple users, they want to talk to each other, they want to communicate or exchange data simultaneously at the same time. So how do we manage this multiple access problem, which is going to be managed by this layer through some different multiple access techniques that we're going to learn. Another important topics in this layer is the addressing. So remember that in upper layer, we have in the network layer, we have the IP address, right? We use the IP address, but here we are gonna use another type of address, which we call MAC address. So this is a link layer addressing to solve some problems. It's different than IP address. As you know, this is called MAC address. And then we're gonna learn some specific protocols and methods in the local area networks, such as Ethernet, VLANs, and so on. And last but not least, institution and implementation of various link layer technologies. Okay, so let's start with introduction, link layer. Here we have some terminology that you need to be familiar with. So host and routers at this layer is called nodes. So we're going to call them as nodes. And another terminology is called links, as you know, is the communication channels that connect the physically adjacent nodes along communication path. So now we are talking about the physical communication. And these can be wired links, wireless links, or LANs. And in this layer, remember in the upper layer and network layer, we have the packet and or datagram. So in this layer, we're going to call them frame. So layer 2 packet is called frame, which encapsulates the datagram. So from now, we're going to use these three terminology: nodes, links, and frames. So in just one sentence, what is the main responsibility of the data link layer? What's the main job of this layer? Is transferring the datagram from one node to physically adjacent node over a link. So this is the main responsibility of the data link layer. is trying to transfer the datagram from one node to the neighbor physically connected, physically adjacent node over a link, and link can be wired or wireless and so on. So, and the datagram transferred by different link protocols over different links. So in practice, that can be a different types of link layer, links and link protocols between source and the destination. It's not that homogeneous. It can be heterogeneous, you know. Like in the first link, you may connect your computer, laptop through the Ethernet to the, you know, to the internet. This is the first link, and then frame relay on intermediate links, and you can access to your. Let's give another example like this. So your smartphone can access to the internet through some links. The first one is the Wi-Fi 8.0.11 link, which is the last link, in order to connect to the Wi-Fi access point at your home. And as you know, Wi-Fi access point also is connected to the wall through the Ethernet or other type of wired link. So what I'm trying to say, in order to you reach from your smartphone to another destination, you may go over different types of links. In the first link, you may have Wi-Fi. In the second link, you may have the Ethernet. In the third link, you may have the fiber optic link, and so on. This is the practical case. And each link protocol provides different services. And as you know, each of them may or may not provide reliable data transfer over the link. So let's have an analogy in order to understand better this context. So we're going to give an example in transportation. Assume that you are traveling from Istanbul to Adıyaman, Kahta, Namrud Mountain. So you want to visit the Namrud Mountain. So what's the protocol that you need to follow? Usually, this is the usual case. There are different protocols or different ways. First, you take a taxi from home to your Sabiha Gökçen airport, and then from the airport, you take a plane from Sabiha Gökçen to Adıyaman airport, and then from Adıyaman airport to the Namrud mountain, you take a taxi or cab. So in this example, tourist is equivalent to datagram. The transport segment is equivalent to communication link. Transportation mode is the link layer protocol, and the travel agent is equivalent to the routing algorithm. Remember, travel agent is the one that draw or plan your complete trip, right, from your home to the Namrud mountain, which is equivalent to the routing protocol. And the transportation mode is equivalent to the link layer protocol that we are discussing. So this is the example that you can map to the network case. Okay, so after this brief introduction, so let's now go to the details of the link layer services. First of all, one of the important services that is provided by this layer is framing and link access. So what's framing? Because we receive the datagram or packet from a network layer from the upper layer, we need to encapsulate datagram into frame. After encapsulation is done, we add some header information as well as the trailer, header and trailer. And then we pass this through the physical layer. And then the second services that is provided by this layer is channel access if the medium is shared, if the channel is a kind of shared environment. And in this layer, we use a new type of address we call MAC addresses. They are used in frame headers so that it can to identify the source and destination. So in this case, the MAC addresses are used in frame. We put this MAC source MAC and destination MAC addresses into the frame headers so that the receiver side can identify, or the intermediate nodes can identify the source and the destination. And note that this MAC address is, of course, different than from the IP address. So the first type of services that is provided by this layer is framing and link access. Another important services that is provided by this is reliable delivery between adjacent nodes. And we learned how to do this already in chapter 3. And sometimes rarely used on the low bit error link. But when it comes to the wireless links, it's not like a wired link that we learned. There may be a high error rates that we're gonna learn in the future. So let's continue on the services that are provided by this link layer. Another important mechanism is called flow control. So it's a pacing between adjacent sending and receiving nodes. And so it helps to flow the data between adjacent sending and receiving nodes. Another important services is error detection, because errors is caused by the signal attenuation and the noise of the system throughout the transmission. And then the receiver can detect some of these errors. And so if detected, there are different mechanisms. Some of them they can correct at the receiver side. Some of them ask the sender to retransmit or drop this frame. So how another important services that is provided is called error correction. So first you need to detect the error, and then another mechanism is called error correction. So receiver in these methods, the receiver identifies and corrects bit errors without resorting to the retransmission. So instead of asking the standard to retransmit the lost or the erroneous bits, instead of that, receiver try to correct these bit errors by itself using these techniques. So duplexing is managed by this layer as well. We have different types of duplexing methods. Half duplex and full duplex are the most popular ones. You know, with the half duplex, nodes at both sender and receiver part can transmit, but not at the same time. So when you say half duplex, sender can transmit and receiver wait. And then when it's done, the receiver can send and wait. But when we say full duplex, both sender and receiver can transmit at the same time. So these are the different duplexing option that is provided by this link layer as a service. Okay. So another question is, what is the link layer implemented? So where is this actually located, this link layer? Because the upper layer mostly consists of software. Okay, router can be part of that as a hardware, but from now on, we may have more kind of hardware or something that we can touch. So the question is, what is the link layer is implemented? The answer is in each and every host. In every host, we have this link layer kind of device. So what is this device? It's called adapter, or also known as network interface card, NIC, or on a chip. So instead of card, we may have a system on chip. So if you want to give an example, Ethernet card, as you see in the slide, this is one of the Ethernet card, or Wi-Fi card, as you see with the antennas, or Ethernet chipset. So these cards, they consist of both link layer as well as the physical layer. So let's look at it. This is our computer, and at our computer we have this network adapter card. You can split into two parts. One of them is this NIC card, network adapter card, which consists of the controller and the physical transmission, physical layer, which is connected to CPU and as well as the memory, of course, through the PCI or other type of bus. So in this card, we implement both link layer and the last layer, physical layer. And this attached into the host system buses in order to communicate with CPU as well as the memory. In summary, the NIC card, network interface card, consists of hardware, software, as well as the firmware. So this is a typical implementation of link layer in practice. So as you see, this is the NIC card where we implement the link and physical layer, and the above layer, which consists of application transport link, network, and some part of the link layer, because in the link layer we have some software, so it's implemented in the CPU. Okay, how these network adapters communicate with each other? We have two hosts, and each host, as you know, has one adapter. Let's call this a sending host, which has an NIC, network interface card, or adapters. And we have the receiving host, which consists of also another adapter, network adapter. So let's look at the steps that we follow in order to send the datagram from sending host to the receiving host. In the sending side, first of all, we encapsulate the datagram into frame. So we receive the datagram from the upper layer, which is the network layer, and then we encapsulate, we package the datagram into the frame. And after encapsulation is done, we add some header information as well as the trailer information. So we add these error check-in bits, okay, for error detection and correction, and some reliable data transfer info, some flow control, and so on. So once the package is ready, the frame is ready, we transmit through the physical link, which can be wired or wireless. And then at the receiving side, we receive the datagram and looks for the bit errors or other using the information in the header in order to check other mechanisms such as flow control. And we extract the datagram and pass this datagram to the upper layer, which is the network layer. So this is how two network adapters communicate with each other. Okay, so after this introduction and learning the main services of link layer, now let's dive into the details of these services, starting with error detection and correction. So we call EDC, stands for error detection and correction bits. And these bits are added as a redundant. So it's not that it doesn't carry any information. So it's not your video or voice or text. It's just kind of a control bits that is used for, error detection and correction purpose. And your actual data is called D, data that is protected by this error detection and correction mechanism. It may include some header fields as well. So error detection is not 100% reliable. It can detect some error, and it can miss some of them. So, but as you see from here, if you look at the frame, it's split into two parts. One of them is D, which is your data that you're trying to transmit. And the other part is called EDC bits, which is for error detection and correction purposes. If you use larger EDC field, this is gonna yield to the better detection and correction, but this is gonna eat from your bandwidth. So as you increase the number of EDC, your number of data is decreasing. So you're eating from your data bandwidth, so which is gonna decrease your data rate. But in some application, if you need a very robust error detection and correction, you should use large number of EDC bits. Okay, how this EDC works? So we receive the datagram, which consists of the data, and then we calculate EDC based on some mechanism and add this redundant bit to the frame, and then we transmit along with data through the physical link, which can be wired or wireless, but note that this link, in either case, they are bit error prone, so they are kind of open to the bit errors. So at the receiver side, you receive this frame, and then which consists of data as well as the EDC. So you calculate the EDC based on your data, as well as, and then you compare with the EDC bits that you received. If the EDC, so if the EDC is equal to the EDC that you receive, then there is no error. But if the computed calculated EDC is not equal to the received EDC, then we declare as an error. So one of the simple error detection method is called parity checking. So, and there are different versions of this parity checking. The simple version of that is called single bit parity. And this has a two version. One of them is called even parity check. The other is called odd parity check. So in this case, this single bit parity check can allow you to detect a single bit errors. So let's give an example. These are data bits that you are trying to transmit, and it consists of some number of ones and zeros. So you calculate number of ones, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, we are using the odd parity check-in. So the number of ones should be odd number. So it's 9. That's why we put 0. If you are using even single bit parity checking, then we need to add one more to make the number of ones as even. So it was 9, and 9 is a odd number. In order to make this even number, we need to add 1 to this field so that we can make 10. And 10 is, you know, is a even number. And this is one-dimensional single bit parity checking. And we talk about parity checking, and odd parity checking consists of, for the case of single bit. Now let's look at the two-dimensional bit parity. This single bit parity can only detect a single bit, but in two-dimensional, you can even, so in this case, we don't know which one is, which bit is corrupted. But in the two-dimensional, we can detect both. We can both detect and identify which bit is actually corrupted. So let's look at an example. So this is assume that we are transmitting these bits is 10101. As you see, what are the number of ones is 1, 2, 3. And we are using even parity checking. That's why we need to add 1 here to make 4, which is an even number. Here we have 1, 2, 3, 4, 4. So it is an even number. That's why we add as a 0 parity bit, because 4 is even number. Here in the third row, we have 1, 2, 3, 3 ones, which is odd number. In order to make even, we add 1 as a parity here. It becomes 4, so that it's even. Now let's look at the row-wise in the the column-wise. Here in the first column, 1 plus 1, 2. We have 2 ones, which is even, so that's why you put 0. In the second column, 1, 2, it's even, so that's why we put 0. Here 1, 1, 3 is odd. We need to make even. That's why we add 1 as a parity to make 4. In other words, to make even, and so on. In the fourth columns, we have 1, 2. That's why we put 0 as a parity, 1, and we add 1 to make even as a parity. So we transmit this one, and during the transmission, assume that this second column, second row, second column, the bit with red color, originally it transmitted as a bit 1, and now it's flipped to 0. Assume that this bit is corrupted during the transmission. At the receiver side, using this two-dimensional bit parity, how do we detect and identify these specific bits? In the second row is 1, 1, 1. So 1, 2, 3. Normally, this one should have a parity should be 1, right? But it's 0. That's why we assume that there's a bit that is corrupted in this row, but we don't know which one. Now let's look at the second column so that we can identify. In the second column, we have 0, 0, 1. So just 1, and the parity is 0. Since we are using the even parity checking, this parity should be either 1. So it's 0. That's why we have an error here. So the intersection of these second row, second column and second row shows that there is an error in these bits. So that's why using the two-dimensional bit parity checking, we detect and even identify which specific bit is corrupted and it needs to be corrected. So, but in the single bit parity, in the one-dimensional single bit parity, we can only detect there's an error, but we don't know which bits is corrupted. If you want to know which specific bit is corrupted, then you should use two-dimensional bit parity. So there are three different methods in this case. The first one, we call it error detection and correction mechanism, and we give you a technique in this case. The second one is internet checksum. Remember, we learned this checksum at the transport layer. So the main job of this internet checksum was detect errors in the transmitted packet. And how it works, let's remember, we treat the segment contents as sequence of 16-bit integers. So we have two 16-bit integers data, and we add them up, sum up, and then we take the ones complement and we calculate the checksum value, and we put this checksum value into UDP checksum field, and then we transmit, remember, this segment. At the receiver side, we compute the checksum of the received segment, and then we have the received checksum. We compare the computed checksum with the received checksum. If the computed checksum is equals to checksum field value, we said that there is no error. And then if they not equal to each other, then the error is detected. So we learned this at the transport layer. Another method is called CRC, which stands for cyclic redundancy check. This is more powerful than, error detection coding. So in this case, we have D as a data. Again, with the CRC method, we calculate some CRC bits, and then we add these CRC bits as a redundant, and we send along with data to the receiver side. So how do we calculate the CRC? We choose R+1 bit pattern generator. So we have a generator polynomial which we call G. Our main objective in this method is choose R number of CRC bits such that based on this division. And the receiver knows this G polynomial, so it received the data and then it applied the division using this G polynomial. If non-zero remainder, error is detected. If zero remainder, then there is no error. So this is a powerful error detection coding that can detect all burst errors less than R+1 bits, of course. And this is popular because it's used in practice by Ethernet that use Wi-Fi and ATM technologies. So let's have an example for the CRC, how to calculate the CRC bits. So this is the mathematical formula, which is equivalent to this. So basically what we are trying to do is simply assume that this is 6 bits our data D, and this is our polynomial G, okay? which is 0, 1, 2, 0, 1, 2, 3, x cubed plus 1. This is a polynomial, our generator polynomial. So we're going to divide this d by g using the binary division. So I don't know, you guys remember or not? So let's go over it together. So we have 1. So if you divide the d by g, we have the g once 1 times g is equal to 1, 0, 0, 1. If you add them up, is 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0. So the remainder is 1, 0 in this case. So if put this down, it becomes 1, 0, 1. 1, 0, 1 doesn't have 1, 0, 0, 1. That's why we put another 0 here. So if you add them up, it's 1, 0, 1, 0, 1, 0, 1. And then we put another 0 here. So now, do we have g in d? Yes. So we have 1 times g, which is 1, 0, 0, 1. If you add them up, is 0 plus 1 is equal to 1. 1 plus 0 is 1, and the remainder is 0, 0. And then we put down 0 here. Note that the number of r in this case is 3. That's why we put 3, 0 here, okay, at the end of the data. So r is equal to 3 in this case. And then so on, you end up with this remainder until you are completed with this number. So the calculated r, which is our CRC, is 0, 1, 1. We put this 0, 1, 0, 1, 1 at the end of these data bits, and we send them together through the link. Okay, so that was about the first mechanism that we use in the link layer, which we call error detection and correction mechanism. Okay, so the second main service that is provided, which is very important, is called multiple access protocols. This is one of the core part of this link layer, as well as the most of the networks. Because in the networks, you are trying to provide the services to the multiple user at the same time. So the question is how we're going to handle multiple user and how we're going to make them happy. So two types of links that we cover. The first one is point-to-point, right? Which is used for dial-up access or between Ethernet switch and host. And we have another one is called broadcast because the medium is shared, right? And this broadcast is used by old-fashioned Ethernet or upstream hybrid fiber coaxial HFC and by Wi-Fi. So as you can see, there can be different types of medium and environment. So the shared environment can be wire, the cable, as you see from here, which is used by the Ethernet. And the shared medium can be air, RF, radio frequency, which is the case for the Wi-Fi. And the shared RF air is a wireless link by the satellite communication. This is the satellite, this is your receiver dish antennas at your home or office that you receive TV channels and so on. As you see, we have the multiple users, in this case in satellite, in the Wi-Fi, in the Ethernet. So we need to support their requirements, their request basically. Some of them request to watch video, the other want to talk to voice, and the other wants to send a text messaging and so on. So we need to make all these client in our case is node, happy. So that's the case for the network. We have the similar situation in our human life, right? So in a family gathering, everybody start to talk to each other, about something, right? And in this case, the medium is the shared air, right? And we use the acoustic or the voice to talk to each other. How people they talk to each other at the same time, there are different, kind of protocols. All we call it rules, basically. So let's start with these multiple access protocols. We said that mostly we have a single shared broadcast channel, which can be a wired, cable, or air. So two nodes, they may talk to at the same time, right? Using this shared channel. Two or more simultaneous transmission can happen by the nodes in the network. In such case, we're going to experience the interference. If we experience interference, we end up with collision. What's the collision? If a node receives two or more signals at the same time. So I'm the router, and there are two smartphones. They want to talk to me at the same time. So, and they use the shared air, wireless links. Once they transmit at the same time, we may experience collision. Okay, so this is one of the important problem in the multiple access protocols, which is called collision or interference. So that's why we need to design multiple access. We need multiple access protocol. Otherwise, people they're gonna keep interfere with each other. They're gonna collide their packet, and they not able to communicate without communication. So we need to come up with some rules, some protocols we call in network, to manage and handle this interference, this situation. Okay, one of the approaches is distributed algorithm that determines how the nodes share channel. How the nodes is gonna share and access this channel, and when and which node is gonna transmit and use these shared resources. And in this case, we are gonna use kind of control channel, which is different than the data channel. Or sometimes there are some technology that use the data channel as a control channel. So before to address to this problem, so what's the problem? We have a multiple access. We have the multiple user, multiple nodes, smartphone, laptops, and computers. They want to talk to a router or access points at the same time. And we need to put them in the order or manage them somehow so that they can, everybody can transmit their packet successfully. Otherwise, they are going to collide to each other, or they're going to create some interference. So what is the idealistic case? What's the ideal multiple access protocol if you were design? So let's assume that we have a broadcast channel which has a capacity of R bit per second. What is the desiderata? What the desired goal? This is the realistic case. When one node wants to transmit, it can send at rate R. If there's just one node in the network and we have the R bit per second link, this one node can use the whole rate, which is R. But when the number of nodes increase to M, when we have M number of nodes, they want to transmit at the same time, each can send at average rate by R over M. So we divide, share equally the capacity, the bandwidth to each of these nodes, which is R over M, because M is the number of nodes that wants to transmit. Let's assume is 5. 5 nodes wants to transmit simultaneously. And I have a R, which let's say 100 megabit per second. So normally in the first step, if there's just one node, it can transmit at the rate of 100 megabit per second. But when the number of node increase from 1 to 5, then I need to share equally. So which is 100 over 5 is equal to 20 megabit per second. Now each node can transmit with the rate of 20 megabit per second. And what I desire is this network to be fully, or this access protocol should be fully decentralized, distributed. So no special node to coordinate transmission, no master node to coordination of this transmission. And I don't want to have a synchronization of the clocks or the time slots and so on. And it should be very simple. So in practice, whatever you design should be simple. Otherwise, it's gonna, lead to some other problem. So 4 requirements for the ideal multiple access protocols. First, when there's just one node, it should be able to utilize the whole rate R. But when we have the M nodes wants to transmit simultaneously, we shared resources by R over M, and it should be fully distributed, no kind of special master node to coordinate the transmission, or no synchronization of the clocks and time slots, and it should be simple to implement. But this is the idealistic case. But when it comes to the practice, okay, that the ideal condition doesn't work, do not work. So therefore, people, they develop different types of practical MAC protocols, medium access control protocols. So let's look at the classification. We have 3 broad categories, different types of MAC protocols. So we can classify into 3 categories. The first one is channel partitioning. In this approach, we have the resource which we call channel, access channel. We divide this channel into smaller pieces. And these pieces can be in time, in frequency, and in other domains. And then we're going to assign this piece to node for exclusive use. Each piece is going to assign to just a single node for exclusive use. That's the first approach. The second approach is random access. So here we don't divide the resources or the bandwidth into the pieces. Channel is not divided. We just let them use, but this approach is allow the nodes to collide to each other, to interfere with each other. But the strategy is that we need to come up with mechanism to recover from the collisions. And the third approach is called taking turns. So in this approach methods, the nodes take turns, but whichever node has a more packet, more data to send, it take this turn longer. So each of these approach has a many different techniques that we're gonna learn shortly. So let's start with the channel partitioning. The first one is called partitioning in time. In other words, we call TDMA, which stands for time division multiple access. So this is our time, and the node is going to access to the whole channel. Let's say we have 100 megabit per second or 120 megabits per second, let's say. And each of these nodes, they have their own time slots. Once their turn comes, so they're going to access and utilize this channel completely. And each station, each node gets a fixed length slot. As you see, their time slot is equal. In this case, we have a 6 time slot within a frame. So one frame consists of 6 time slots, and each slot is for a node. So each node access to the channel using a fixed length time slot when their turn comes. And some of the nodes may not use their time slot. So in this case, there may be some unused slots, which is going to stand as an idle. In this case, number 2, 5, and 6 slots are idle. So in other words, they are not utilized by their nodes. But the number of 1, 3, and 4, as you see, this node has some packets, and they transmit packets in these time slots. So what's the advantage of this technique is that once a round comes to a node, it can access to the whole channel, let's say 120 megabit per second, and then they can utilize completely these channel resources. But the main disadvantage is that you have to wait your turn. So in this case, we have 6 number of nodes. So the first one is going to transmit complete, then the second start, then the third, then the fourth. So the number 1 has to wait until it come back after the 6 node transmission is completed. So you have to wait the others basically. And the time of the transmission is limited to the time slot that is allocated. This is the disadvantage of this method. The second one is called FDMA, which stands for frequency division multiple access. So we talk about channels. In our case, let's say 120 megahertz. So in the first one in TDMA, once your turn comes, you can utilize this whole 120 megahertz. But in this case, we split the channel into the number of sub-channel. So the channel spectrum is divided into frequency band. We partition the channel in frequency domain, in other words. And each node is assigned a fixed frequency band. So let's say in this example, we have 6 nodes, and the total was 120. 120 megahertz divided by 6 is equal to 20 megahertz. So we assign exclusively this 20 megahertz to each of these nodes. So each node gets a fixed frequency band. In our example, is 20 megahertz. Similarly, there can be unused transmission time in frequency bands, so which can go idle. In this example, again, the number 2, 5, and 6 frequency bands are not utilized, so they're idle. But number of 1, 3, and 4 are utilized. We see the some packet transmission. So what is the, if you compare the FDMA with the TDMA, what are the advantages of this FDMA? So you don't have to wait, because as a node you have exclusive, that is just belong to you, a sub channel. You don't have to wait turn so that it comes back to you and then you can transmit. Anytime you can transmit your packet. But the disadvantage of this, the bandwidth that is utilized is very small compared to the TDMA case. In TDMA, okay, you have to wait all the nodes transmit is completed. So when it comes back to your turn, you can access to the whole, in our example is 120 megahertz. But in this case, we have 6 users, so you're only using 20 megahertz. So that means in TDMA, for instance, your rate is going to be 120 megabit per second. In this case, in FDMA case, it's going to be 20 megabit per second. So that's the main disadvantage of FDMA, but it has an advantage that you don't have to wait other nodes to complete their transmission.